We'll continue generating the paraboloid. So paraboloid equivalent, paraboloid approximation, polynomial approximation to any polynomial function. So if I have a polynomial function fx, if I have a polynomial function fx, then what would be its equivalent as far as paraboloid is concerned? Paraboloid is concerned. So we are talking about 3D. So 2D, we saw that if I have any function fx, then if I want to convert this function as an approximation to fx as another function at gx, fx, gx, fx is any function over x, then gx is any function over x. Fx is any function but gx. Gx is a parabola. So converting any function fx to a parabola function, that is the concept. If I have fx, if I have gx, and gx is in form of kx square, then in fx, if I differentiate fx, then I get set of points where set of points means x0, x1, x2. I get set of points where fx is f dash x, means the differential f dash x dfx by dx at point x0, x1, x2, x3 are 0. If I have differential as 0, then at those points there is no slope. So either it is maxima or minima. If I have a function fx and at some point in independent variable that is along x-axis, if I have dependent variable that is y-axis, so at some points in x independent variable, if I have points on the curve as x0, y0, x1, y1, where the differentiation is 0, then those points are not simple points. Those are called extreme points because there the differentiation is 0 and they are maximum or minimum. Like if I have sine wave, okay, so if I have sine wave, then sine t or sine x when x is equal to pi by 2 or minus pi by 2, then there x equal to pi by 2, then y is 1. X equal to minus pi by 2, then y is minus 1. dfx by dx at x equal to pi by 2 is 0, whereas dfx by dx when x equal to minus pi by 2 again 0. So if it is a sine wave, if it is a sine wave, then at pi by 2x it is maximum, whereas sine wave at minus pi by 2 it is minimum. So when differentiation of a function fx is 0 at point x0, then at x0 the function attains either maximum or minimum. So in some closed region, if I transform that equation fx into gx, where gx is parabolic function, then looking at the coefficient of x square, parabolic function means gx equal to kx square. If that is true, then looking at the coefficient means k, the sign of k, I can immediately say that whatever the extreme point we are seeing, this is maximum or minimum. So that is the concept. So if it is positive, then it is minimum. If it is negative, then it is, if it is negative, then that is maximum. Now we are into same kind of phase, and now we are into 3D. Independent variable in 2D is x and dependent variable is y. Now independent variable is x and y, whereas dependent variable is z, fxy. Okay, now I have surface instead of line. If I have a surface, then surface can also be maximum and minimum. Okay, like mountain has a peak and then it goes down, and then peak. Okay, so it is like, means it can be seen. You can see any mountain. If there are two mountains near to each other, then there is a peak and it will come down, then there will be another peak. So maximum, minimum, maximum, it is something like that. So if I have, this is a typical case of 3D where we have surface. It's not a line, we have surface. So mountain, if I see the mountain, then if I cut xz plane, then again it is a peak. If I cut along yz plane, it is a peak again. If I see the minimum x, z and y, z plane, it is minimum again. So what is the equation, simplest equation? If I see the 2D, then 2D, the monomial equation for the function fx is x to the power 1, whereas polynomial function, binomial is x to the power 2, and polynomial is x to the power n. Here, the monomial function, monomial surface means flat surface. Monomial line means, monomial curve means straight line. X to the power 1 means a straight line. Here x to the power 1 and y to the power 1. So simplest surface I can take as x plus y. If it is x plus y, then this is a surface. This is fx. Fx equal to x plus y. If fx equal to x plus y, then what is gx? Gx means, can we now convert this surface into a paraboloid? Paraboloid. Any fx I want to convert into paraboloid. Paraboloid means I have a curve like this along xz plane, and I have cut. This is x-axis, this is y-axis, and this is z-axis. So in xz plane, this is parabola. In yz plane, this is parabola. If I rotate completely, it becomes paraboloid. If it becomes paraboloid, then equation of paraboloid is z equal to k x square plus, or alpha x square plus beta y square, or I can say x square plus y square. If that is the case, x square, alpha x square means in xz plane, it is alpha x square, like 2D. Beta y square in yz plane, beta y square, same, beta y square, 2D. If we combine both, then it becomes alpha x square plus beta y square. Now, if, or in other form, if I can say, if it is like that, where alpha and beta both are positive, alpha positive, beta positive, it will come in a form x square plus y square. If that is the case, then paraboloid is minimal paraboloid. Okay, and if it is positive, then if it is positive, then it minimal. If it is negative, then it is maximal parabola. So why we are hitting our head against parabola and paraboloid? Because parabola are peculiar in a sense that there is only one extreme point in the parabola, always one extreme point, and then beyond that it grows to infinity. That extreme point can be minimum, that extreme point can be maximum. So if I have a line equation of or a surface equation where I know that at this point the surface is extreme point, so extreme point for the surface where the independent variable is x comma y. If there are two independent variable in the surface, then I can differentiate along x-axis, that is dz by dx. I can differentiate along y-axis, dz by dy. I mean, I am trying to find the gradient, that is differential value is 0 in xz plane, differential value as 0 in yz plane, where these are 2D and 2D, not 3D. So in xz plane, what is the differentiation? If it is, then I set it to 0, dz by dx to 0, dz by dy to 0, and then I try to find x and y value, and if I call it x0, y0. Now x0, y0, and z0, whatever z comes. If I see that point in the surface, then that point is extreme point. Either it is maxima or it is minima. So I have to know that point is maxima or minima. That is the concept. If I have two partial derivatives, dz by dx and dz by dy, if I set both partial derivative to 0, then I get a value of x and y. At that point, I know that slope along x-axis and slope along y-axis both are 0. If that is the case, then it is parallel to xy plane. If that is the case, then at that point it is either maxima, surface is maxima, or surface is minima. If that is the case, then it is maxima or minima we can find if I convert that surface region along the extreme point to a paraboloid. If it comes as paraboloid, quickly say, knowing the coefficient of the paraboloid, I can immediately say that is a maxima or minima. So this is the concept that we are pursuing. Now it comes like what we have to do, how I can proceed. So if I have now it comes that any fx, if in any fxy rather in 3D, any fxy, how I can convert to gxy, where gxy is parabola. So fxy, if it is a flat surface, x plus y, then certainly flat surface cannot be converted into a paraboloid. That is monomial cannot be converted to polynomial. Okay, so straightforward. But anyway, if I have a flat surface fxy, can I convert this flat surface to another flat surface which is represented through differential equation? Exact matching. That is the idea. So if it is x plus y, then if I differentiate it partially along x-axis and y-axis, I keep differentiating it till there is no independent variable left there. That is the idea. So if I do dz by dx, then it comes as 1. X plus 1 means x. Y is gone. So x means 1. Now this is a scalar value. So maximum I can go dz by dx. dz by dy is 1. Now if I want to x plus y, if fx and gx I want exactly same. Gx is exact replica of fx, where right now Gx is a equation of a surface through differential equation. If I want that, what I have got from the fx equal to x plus y, then I got dz by dx means fx. I have two functions fxy and gxy. Now fxy is a plane surface. Now I want gxy exact replica of fxy, where gxy is defined in terms of differential equation, algebraic. Now through fxy I have fx, that is dz by dx. Through fxy I have fy, that is dz by dy. Now can I have another function gxy, where gxy equal to dz by dx into x plus dz by dy into y. If that is the case, this is also called tangential surface. If dz by dx is a scalar value calculated at any point x0 and dz by dy is a scalar value that is calculated at any point where y equal to y0, then whatever plane I am getting dz by dx x plus dz by dy y, the plane what I am getting, that plane is tangential to the curve through which I am getting this, calculating this at point x0, y0. But anyway, now there is no curve and it is a straight plane. So if it is a flat plane fxy and there is another plane gxy and it should be exact replica of it, then dxy should be dz by dx x plus dz by dy y. If dz by dx is 1 and dz by dy is 1, then gxy is x plus y. We are getting exact replica of the fxy in gxy if gxy is dz by dx x plus dz by dy y. If fxy equal to x plus y to the power 2, x plus y whole square. Now make a replica of fxy in gxy as far as differentiation is concerned. So dz now that turns up to x square plus y square plus 2xy, or x square plus 2xy plus y square, x plus y whole square. Now from flat plane to curved plane I have got. Now x square plus 2xy plus y square. If I do dz by dx, then it turns to 2x plus 2x. If I do, I'm sorry, 2x plus 2y, y square is gone. If I do, but there are independent variables. Now, I will do differentiation again, dz by dx, again d2z by dx square. It will come as 2 and 2y is also gone. So, my motive is over. So, d2z by dx square maximum I can do, and its value is 2. d2z by dy square is again 2. There is another term called 2xy. So now if I do dz by dx, it is 2y. Now if I do dz by dx into dz by dy, I mean dz by dy of dz by dx. I do dz by dx, whatever comes, again I do dz by dy on top of it. So we call it fxy. dz by dx, whatever I get, I do dz by dy of that value. So d by dy, so d of dz by dx by dy. If that is the case, then dy, then we also call fxy. dz by dy, by dy, and d by dy of dz by dx, okay, or fxy. If that is the case, then it will turn the x square will go away. First I differentiate with x, then it is 2x. If I differentiate with y, then it is 0. Same y square will go away. 2xy, first it will become 2x, 2y, and then it will become 2. So fxy, f, and down we write xy, not f in bracket x comma y. So this is dual differentiation. First along x-axis, partial, and then along y-axis, or dz by dx, dz by dy. This is what we will call it. So dz by dx, dz by dy, or fxy is 2. Now we have three derivatives here which brings a scalar here. One is d2z by dx square, or fxx, or d2z by dy square, fyy, or d d dy of d by dx, or fxy. Now both are 2, 2, 2. If I want to reproduce this fxy to gxy, reproduce f bracket x comma y is a function to g bracket x comma y, fxy to gxy. If I want to get, and what I have in my hand is fxx, fyy, and fxy. So now how I can reproduce? So I can reproduce in a fashion that d2x by dx square into x square divided by 2. So d2x by dx square is 2. So 2 by 2 gone. So it comes as x square plus fxy plus fxy, or d by dy of dy dx, d by dy of dz by dx, d by dy of dz by dx, fxy. So fxy is 2. So d fxy into x into y divided by nothing, means by 1, or factorial 1, factorial 1, whatever. So fxy into x into y. So fxy is 2 and then xy. So 2xy plus fyy d2y by d2z by dy square into y square divided by 2. It will come to y square. So same we will get x square plus 2xy plus y square. Please mind it that whatever we are talking now is differential way to achieve something. We are differentiating at one place and we are trying to achieve something, but we have other way also, that is integral way. So if we are proving something through differential way, later on we will prove it through integral way also. Okay, so what we are trying to do now is, if I have any function fxy, then what will be its polynomial variation as gxy. This is mainly we are trying to do. So if fxy, function fxy equal to x square plus 2xy plus y square, or x plus y to the power whole square, if that is the case, then gxy equivalent would be d2z by dx square. Means I have calculated d2z by dx square over fxy, d2z by dy square over fxy, and d of dy of the dz by dx fxy. If I have these three things, then I can reproduce fxy function as function gxy exactly in a form that d2z by dx square into x square by 2 plus d of d by dy of dz by dx into xy plus d2z by dy square into y square by 2. If that is the case, then exactly we can replicate fxy to gxy. What about if it is x plus y to the power 3? If it is x plus y to the power 3, means x cube plus y cube plus 3x square y plus 3yx square. I mean, we can get it x plus y to the power 3 as x plus y to the power 2 into x plus y. X plus y whole square into x plus y. That will come as x square plus 2xy plus y square as a whole multiplying with x plus y. So it will come as x cube plus 2x square y plus y square x. Then it will come again with a yx square plus 2xy square plus y to the power cube. More or less it will come as x cube plus y cube plus 3x square y plus 3yx square. So that is the concept. Now if I have fxy as function, that is x cube plus y cube plus 3x square y plus 3y square, then how I can reproduce it as another function gxy, where I have the information from fxy as differential partial derivatives, derivative along x-axis, derivative along y-axis, and derivative along x and y-axis, that is fxy. d of dy, d by dy of dz by dx. Now, if it is x cube plus y cube 3x square y 3yx square, then how if I do partial derivative along x-axis, the idea is how I can get a scalar out of it. So if I do first derivative, then it will along x-axis, then it will come as 3x square plus y cube will go away, and then there it will be 6xy x square 3x square y means 6xy, and there again 6y square. If I do derive again, then it will become 6x and plus 6y, and then nothing, it will go on. Now if I derive again d3z by dx square, then it will come as 6 and then nothing. So d3z by dx square is 6. d3z by d3z by dyq is again 6. 3 into 2. Now the two terms, what we have a 3x square y plus 3yx square. So if I do d2z by dx square, then that will become 6y and then nothing. Again, if I do d2z by dx square, and again if I derive as d of d2z by dx square dy or fxxy, then it will come as 6. Other thing all will go away. If I do fxyy, f then down xyy, first differentiate along x-axis dz by dx, then whatever comes differentiate along y-axis d by dy of the dz by dx, then again differentiate along y-axis with d2y by dy square of dz by dx, then it will come as 6 again. So fxxy is 6 and fyxx is 6. Everything is 6. But I have 4 terms now. dxxx, I mean fxxx, d3z by dxq, d3z by dyq, d d by dy by d by dy of d2x by dx square, and d2y by d2y by dy square of dz by dx. Okay, all are 6. Now this is fxy. From there we retrieve four partial derivatives. Now I have to reproduce this as gxy. Now gxy should be exactly same with these 4 partial derivatives. What would be the equation? Then equation would be d3z by dxq into xq divided by factorial of 3, because we received 6, 6 has to be cut down, plus d3y by d3z by dyq into yq divided by factorial of 3. Then 6 will cut out. So it will become xq plus yq. This is what we want. Now, beyond that, we have fxxy. fxxy means d by dy of d2z by dx square. fxxy into x square plus y divided by 2, plus fxyy into xy square divided by 2. Okay, so if I do so, then fxxy is 6 divided by 2 will become 3. So 3x square y plus 3yx square. So the gxy is now x cube plus y cube, 3x square y plus 3yx square. Now we can reproduce, we have copied exactly fxy by gxy, where from fxy I retrieved the four information: fxxx, fyyy, fxxy, and fyxx. F fxyy, fxxx, fyyy, fxxy, and fxyy. If I have these 4 information from fxy, then exactly I can recreate it same function in gxy. If I have gxy is fxxx into x power 3 divided by factorial of 2 plus fyyy into y to the power 3 divided by factorial of 3 plus fxxy into x to the power 2 into y divided by factorial of 2 and factorial of 1 plus fxyy into x into y square divided by factorial of 1 into factorial of 2. If that is the case, then gxy is exactly x cube plus y cube plus 3x square y plus 3y square, 3xy square. So we can replicate it in 3 dimensions. This is what. So now we can proceed x plus y to the power 4 and x plus y to the power n, like this, or x plus y plus z, or x plus y plus z to the power 2, x plus y plus z to the power n, or x plus y plus z plus k, or x plus y plus z plus k to the power 2, x plus y plus z, x plus y plus z plus k to the power n. If this is fxy zk, then what would be gxy zk when we have fxxxxxx, fyyyyyy, and then fx square fxxxxy k, fxxxyykkk, means as per the whatever we have. If I fetch all the partial derivative and cross partial derivative, we can say as fxy. With those partial derivative, we can reproduce the polynomial in the gxy. So that is the concept of the kind of as far as polynomial equation in 3D is concerned. Now we had x plus, now consider the kind of, if I have x plus y to the power n, x plus y to the power n, x plus y to the power n. If that is the case, then I can reproduce it as we said, f x x x up to n plus f y y up to n and so on. Now consider that 3D surface is not x plus y to the power n. What we saw, if it is x plus y, if it is monomial, it is x plus y, then here we have dz by dx into x plus dz by dy into y. If it is x plus y whole square, then we have d2z by dx square, x square by 2 plus d2z d2z by dy square into y square by 2 plus 2 plus d of dy of dz by dx into x into y. If this is for x plus y whole square. Now, if it is x plus y power 3, then we saw it is fx xx into x cube divided by factorial of 3. Fyy into y cube divided by factorial of 3, factorial of 3, plus fxxy into xy by divided by into x square y divided by factorial of 2, plus fxyy xy square divided by factorial of 2. Like that we can carry on. So I have x plus 1 monomial fxy, or x plus 1 whole square, or x plus 1 power 3 up to x plus n square. What about if I have mixture of everything? Okay, now I have fxy, that is mixture of all monomial, means flat surface, up till all the surface. If that is the case, if it is mixture of all the things, now can I reproduce fxy as gxy as a flat surface one? That is the concept. If I have fxy as a mixture of x plus y, means x plus y to the power 1, x plus y to the power 2, x plus y to the power 3 plus like x to the power n, complete mixture. Can this mixture I can reproduce in gxy only as a flat surface, not more than that. Then I will calculate fx dz by dx at any point x0. Then dz by dy at any point y0. So I have dz by dx at any point x0, dz by dy at any point y0. If that is the case, then gxy, the flat surface equivalent of fxy, that is gxy, would be dz by dx into x plus dz by dy into y. If that is the case, then dz by dx, whatever I had calculated at x0, that scalar I will put that scalar into x plus dz by dy scalar into y. So this is a flat surface equivalent of highly complex 3D surface, that is fxy. So certainly they cannot be same. If I have highly complex surface in fxy and I am trying to reproduce it as a flat surface, certainly they would not be same. But at x0, y0, where I have calculated the partial derivative, at that point they would touch each other. If this is a surface and there is a point x0, y0, x0, y0, z0, rather I can say, then the flat surface where it has a point at x0, y0, z0, there they would touch each other. So fxy and gxy, they are exactly same at point x0, y0, z0. Otherwise, they are different. Now, if fxy is a function that is in term of x plus y, then x plus y whole square plus x plus y cube and so on. If I want to represent this function as in power of 2 as gxy, I want full polynomial equation in a power of 2, only 2. Gxy is only 2. So gxy would be d2z by dx square into x square divided by 2 plus d2z by dy square into y square divided by 2 plus d of dy of dz by dx into x into y divided by 1 into 1. So if that is the case, then if I have fxy and gxy, then gxy is trying to be replica of fxy, but it's not possible. Fxy is a highly complex curve, and gxy only looks like it is a paraboloid. It is a paraboloid. So a power of 2 only. But when we have calculated d2z by dx square, d2z by dy square, and d by dy of dz by dx, three partial derivative, and if I calculate this at point x0, y0 in fxy, then these are scalar. If that is true, then I receive dxy in form of some scalar value into x square plus some scalar value into y square plus some scalar value xy. Now, these two fxy and gxy, are different. Means even though gxy is replica of is trying to be replica of fxy, but they would touch each other at point x0, y0, z0. So one complex surface and one paraboloid, but they would touch each other at point x0, y0, z0. That is the concept. Now they are same at that point. Now can I represent fxy, that is full polynomial function, as gxy full polynomial, not in the power of 1, power of 2, full polynomial function. Then gxy would be combination of everything. So fx, f and down x, not f as a function, means dz by dx. I'm trying to say dz by dx. Fx into x plus fy into y. This is first part. Second part is fxx into x square by 2 plus fyy into y square by 2 plus fxy into xy. This is second part. Third part is fxxx into x cube divided by factorial of 3 plus fyy into y to the power 3 divided by factorial of 3 plus fxxy into x square by y, x square into y divided by factorial of 2 plus fxyy into x into y square divided by factorial of 2. This comes as x plus y power 3. So x, so gx, first x plus y whole square, x plus, like this we can carry on. This is the representation of the polynomial representation of fxy. So if I have fxy and if I calculate all the possible partial derivative, then I can reproduce fxy as gxy as the first 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 level partial derivative, second level partial derivative, third level partial derivative, fourth level partial derivative, and keep adding like this, then dxy should be exact replica of fxy. That is the concept. So dxy is now dz by dx into x plus dz by dy into y. 1, that is the polynomial of the degree 1, which monomial, plus polynomial of degree 2, d2z by dx square into x square by factorial 2 plus d2y by y is d2z by dy square into y square by factorial of 2 plus d of dy of dz by dx x into y by factorial of 1 factorial of 1. This is the second degree polynomial. Now third degree is d3z by dx cube into x cube by factorial of 3, d3y by d3z by dy cube into y cube factorial of 3 plus d of dy, d by dy of d2z by dx square into x square into y factorial of 2 plus d2y by dy square of d2 by dy square of dz by dx into x into y square of factorial of by factorial of 2. Keep doing like this. So I have got a gxy. How we have got gxy? Polynomial equivalent approximation of any function fxy. So fxy, we started the discussion with the polynomial function. Now it can be exponential, it can be sinusoidal, because we are interested in partial derivative. We are not interested in anything else. So if fxy is any function we just fetch partial derivative. Like if I have a building, then it is standing on top of four pillars only. So only four pillars are important, not all the bricks. If I have billions of colors, then I am interested only in red, green, and blue. That's it. With that, I can reproduce everything. So from all full color domain, I try to fetch red, green, and blue component. With that, I can make billions of colors. Like that, if I have any function fxy, from that we fetch all the partial derivative. If I have set of partial derivative, then I can reproduce fxy as another function gxy with partial derivative. So the polynomial equivalent in multivariable case, as far as concerned, then we keep calculating all the partial derivatives. Fx, x, 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 fy, y, 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 fx, x, 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 y, 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 all partial derivative. And then you reproduce the gxy in this fashion. First for the power of 1, 2, 3, 4, like this. So we started from scratch and now we came to gx like that. Now I'll take one example in 2D, not in 3D. Like if I have a function fx equal to sin x, where x is radian in angle. Fx, function of f over x is sin x. Sin pi by 2 is 1 and sin minus pi by 2 is minus 1. Now, can I reproduce fx with gx as, as a kind of polynomial equation? If that is the case, then I'll calculate first dfx by dx, d2fx by dx square, d3fx by dx cube, d4x by dx power 4, like that. Now the gx, what we saw there is gx is nothing but f d fx by dx into x plus d2 fx by dx square into x square by factorial of 2. Then d3 fx by dx cube into x to the power 3 by factorial of 3. Keep doing like this. This would become the equivalent polynomial equivalent of the fx. So dfx by dx is cos x. So cos x at pi by 2 is 0. So first part is 0. Then d2 fx by dx square into x square by factorial of 2. So first differentiation is cos x, then differentiation is minus sin x. So minus sin pi by 2 is minus 1. So minus 1 x square by 2 plus d3 fx by dx cube into x cube by factorial. Keep doing like this. Then whatever comes, this is the polynomial equivalent of the function fx. So this is what it is. Now if I keep up to two variable one, not beyond that, then it will become minus x by 2, minus x square by 2. If fx is sin x, then equivalent of it as a polynomial equation gx is d2 fx by dx square into x square by 2, because d dfx by dx into x plus d2 fx by dx square into x square by 2, and keep on I am removing up to here only I want. Then if I see the extreme point where x equal to pi by 2 and minus pi by 2, then at those points dz by dfx by dx is 0. So only d2 fx by dx square will come into picture. So when we see at pi by 2, that pi by 2 cos is 0. Pi by 2 cos, then double differentiation, first sin x to cos x, then cos x to sin x back, minus sin x. So d2 fx by dx square is minus sin x into x square by 2. So minus sin x at pi by 2 is minus 1. So minus x square by 2. So this is typically a parabola G where minus x square 2 is the equation. So it is negative. The coefficient is negative, means this parabola has negative means maximum. So parabola is maximum at pi by 2. Means sin x is maximum at pi by 2. Now if I calculate as minus pi by 2, then I have double differentiation of sin x is minus sin x. Then at minus pi by 2, it will be minus into minus means plus. So plus x square by 2 means coefficient of the parabola is plus, so it is minimum there. Same thing we can apply in the 3D. That is the concept. Now, if I have fxy any function and equivalent polynomial is gxy, then if I remove everything, only keep up to the 2 degree, second degree, then I have dz by dx into x plus dz by dy into y, first one, plus d2z by dx square into x square by 2 plus d2z by dy square into y square by 2 plus d of d by dy of dz by dx x into y by factorial of 1 factorial of 1. Okay, now if I fxy, I know that at point x0 y0, x0 y0, it is it is extreme point, means the partial derivative along x-axis and partial derivative along y-axis, fxx and fyy, fxx and fyy. If both partial derivatives, I'm sorry, if I have a function fxy and single partial derivative along x-axis, that is fx, single partial derivative along y-axis, that is y, fy, dz by dx and dz by dy, if both are 0, then that point on the surface, that is x0, y0, z0, if that is the point where dz by dx and dz by dy is 0, then that point is extreme point. There is a curve and it molds there. So that is maximum or minimum. We have to find that is maximum or minimum. I have what from fxy, what information I have fetched is dz by dx and dz by dy, that is 0. So from there we have fetched x0, y0. So at x0, y0, if I calculate dz by dx and dz by dy, it may be a algebraic equation again. If I set it to 0, I get xy value. If I set it to 0 dz by dy, then I get x and y. So those x, y and y points, I know that fxy has extreme point. Those extreme points are maximum or minimum that I want to calculate. Now fxy equivalent of gxy up to power of 2 only we are calculating. That is dz by dx x into dz by dy y plus d2z by dx square into x square by 2 plus d2z dy by dy square into y square by 2 plus d of dy of dz by dx into x and y by factorial of 1. So, if that is the case, then dz by dx and dz by dy is 0, because we are trying to find the gxy equivalent at the extreme point. So, dz by dx is 0, dz by dy is 0. So, gxy, dz and dy, dx and dz by dy, this is also gone. What is remaining in gxy is fxx, f and down xx means d2z by dx square. Fx x square by 2 plus fyy into y square by 2 plus fxy into xy by 1. So this is what is remaining. Now gxy is a kind of binomial function. Now idea is that I have to convert this function into paraboloid, so that knowing the coefficient, so this paraboloid whatever we have, fxx at point x0y, where it is extreme point, fyy d2z by dy square is a scalar value at point x0 y0, fxy means d of dy of dz by dx at point x0 y0 into xy. These values are calculated, these partial derivatives are calculated at point x0 y0, where it is extreme. Now if I have got fx x square by 2 plus fyy y square by 2 plus fxy x into y, then can I rearrange this algebraic equation into a paraboloid, so that looking at the coefficient, quickly I can say that the extreme what I have seen at x0 y0, there I have calculated the partial derivative. That extreme point is maximum or minimum. That is the concept. Now, if I want that, then the x square, y square and xy, this function is turned into another algebraic equation similar to where we have ax square plus bxy plus cy square. If that is the case, then I can rewrite as a outside and then inside that power of two terms a and then full bracket inside that power of two terms, because paraboloid equation is x square plus y square or alpha x square plus beta y square. Here we are trying to do the same thing. So a I'll keep out and power of 2 square that I'll keep inside. So 1 is x plus b by 2ay to the whole square. So this is first whole square. Second is c by a minus b square by 4a square in bracket y square. So this is another square. So one square and another square. Now the first square is all right, but second square, that is y square, has coefficient of c by a minus b square by 4a square. If I solve it, then it becomes 4ac minus b square by 4a square. So, so the full term is a and in braces x plus b by 2ay whole square, that is first whole square, plus 4ac minus b square divided by 4a square y square. Now this is the typical case of paraboloid where it is like alpha x square plus beta y square. Now the alpha x square plus beta y square if I take, then or if I say that k outside k and inside that x square plus y square, but y square has coefficient as 4ac minus b square divided by 4a square. So 4a square is all right, it is always positive, but 4ac minus b square is dicey, it may be positive or negative. This is first thing. What is ABC? Ax square plus b plus bxy plus cy square. Equivalent here in gxy, where it is fxx x square by 2 plus fxy xy plus fyy into y square by 2. So a is fxx by 2, b is fxy, and c is fyy by 2. Now if I see that equation again, a into in bracket x plus b by 2a y whole square plus 4ac minus b square by 4a square into y square. Then y square has coefficient as 4ac minus b square. If 4ac minus b square is positive, then both square has positive coefficient. Now it is completely dependent upon the outside a that is kept there. If a is positive, then it is a minimal paraboloid. Now it is come to a paraboloid equation where net coefficient is a. If that is the case, if a is positive, then extreme case what we are talking about is is kind of minimal paraboloid, means there it is minima. If a is negative, then it is maxima, but dependent upon the coefficient of y square, that is 4ac minus b square. If 4ac minus b square is negative, then it comes gxy, it comes in a form as x square minus y square. If it is positive, then it is x square plus y square. Now, if it is negative, then it comes as x square minus y. This is called saddle point. Along x-axis, it is minimal paraboloid, and along y-axis, it is negative, means it is maximal paraboloid. So x0, y0 point in one direction, it is like this, and x0, y0 point other direction, it is like this. So it is like this and like this. So it is like a saddle that is kept on the horse. So that is neither maxima nor minima. So if 4ac minus b square is positive, then it comes in a term as a inside bracket x square plus y square. Now if a is positive, then it is minimal paraboloid, and if a is negative, then it is maximal paraboloid. This is minimal paraboloid where we have minima. This is maximal paraboloid where we have maxima. But if 4ac minus b square is negative, then it comes in a form of a inside that bracket x square minus y square. Along x-axis, it is minimal paraboloid, and along y-axis, minus y square maximum paraboloid. So x0, y0 point where we are finding this is a minima or maxima, then at that point, it is neither minima or it is both minima in one direction, maxima in another. It should be both in same way. Then now we can say that it is neither maxima nor minima. If b square minus 4ac is 0, then we have come to equation where a into x plus 2x plus b by 2a y to whole square. A inside bracket x plus b by 2a y into whole square, because after that it is 0. If 4ac minus b square is 0. Now it is dependent here what it is. It may be maxima, it may be minima, or it is undefined. Anyway, now we learned that if gxy we place up to two power polynomial can be of any power up to 2 power only, then first power becomes 0 if we are trying to find if our extreme point is maxima or minimum, because dz by dx and dz by dy is 0. Only second part, that is power of 2, remains, and that is nothing but d2z by dx square x square by 2 plus d2z by dy square into y square by 2 plus d by dy of dz by dx x into y by 1. If that is the case, then that is equivalent to a polynomial equation or binomial equation ax square plus bxy plus cy square. That can be represented as a paraboloid. So gxy is a paraboloid now. Now, looking at some coefficient, I can say this paraboloid is a maximal paraboloid, minimal paraboloid, or neither maximal or minimal, or it is undefined. If that is the case, then if I have fxy function and the points where dz by dx and dz by dy or dfxy by dx or dfxy by dy, at those points, if those differentiation is 0, means if dz by dx and dz by dy is 0, if that point is x0 y0 and z0, at x0 y0 z0 we have extreme point. Now fxy equivalent of gxy, we saw that it is fxx x square by 2, fyy y square by 2, fxy x into y, plus monomial is fx x plus fy y. So fx dz by dx and dz by dy are 0. So it is only the binomial we are getting. That can be represented as a paraboloid, and quickly paraboloid I can say that it is maxima or minima, means if I am calculating the paraboloid now at point x0 y0, that is in contention that it is maxima or minima. These are extreme points. At that extreme point, I calculate the gxy, and we rearrange the gxy in a form of alpha x square plus beta y square, and then we try to find that if this paraboloid is maximal paraboloid, minimal paraboloid, it's a saddle point, or it is undefined. So nice, right? Otherwise, what is the way that if it is a 3D, then what is the way that quickly I can find out that the extreme points where dz by dx and dz by dy are maximum and minimum? We have to draw contours now. For fxy, we have to draw contours. And contours, what the point which are the extreme point, around the point we are drawing contours. And around the contour, I have to see that contour is going up, contour is going down. If it is going up, then it is minimal point. If it is going down, it is maximal point. Or if in one direction it is going up, other direction it is going down, this is a saddle point, or if it is an undefined contour. So rather than drawing contour, just calculate the dual derivatives and quickly find out that looking at value of a or 4ac minus b square, it is a maxima or minima. So we tried that we could do some example today. Certainly we will do next time. We will take some example and we will calculate a and 4ac minus b square, and quickly I'll say it is maxima or minima. So we'll see that.